So this is chapter 2, and it's about observing the sky and some history. We're going to start out with, I'm just going to give you a vocabulary list here, and you just need to know these words or phrases. We'll work on them and explain them as we go through the chapter. So I'll just read them off. Celestial sphere, celestial equator, celestial poles, circumpolar, ecliptic, deferent, epicycle, geometric, heliocentric, parallax, precession of Earth, retrograde motion, astrology, apparent magnitude, zenith, meridian, latitude, longitude, right ascension, and declination. There'll be other words in there, but those are some that I'm just drawing your attention to. And you may know some of those already. You've probably heard of astrology if you don't know exactly what it is. We're going to talk about the sky and sort of how it looks the way it looks. We're going to start by sort of defining the main features of the celestial sphere. And so I'm going to pull up some pictures of these in a second. But if you think of yourself as an ancient person and you looked out into the sky at night, you would see all these stars and things. And they imagined them as being in a giant sphere that we were looking at from the inside. And so if you imagine all the stars are dots painted on the inside of a sphere, then that sphere that you're looking out into is called the celestial sphere, and it surrounds the Earth. It's of course imaginary, but we still use it and talk about it as a convenient way of identifying regions of the sky. As we'll talk about later, we kind of divide it into constellations so that we can talk about different regions of the sky. You'll hear the phrase, oh, there's a comet in the constellation Orion, and that kind of tells you where to look for the comet. The celestial sphere has an equator, which is a projection of the Earth's equator. It has a polar axis, just like the Earth has a polar axis that it rotates around. And the celestial sphere has a polar axis along the Earth's axis. The Earth's north pole points at the north pole of the celestial sphere, and the North Star Polaris is at the celestial North Pole. And so if you imagine the Earth's equator just projected outward, then it creates sort of an imaginary equator around the celestial sphere. Our north and south pole point at the north and south pole of the celestial sphere. And so the Earth rotates inside the celestial sphere, you might say. And so let me just pull up a picture or two here. So you can sort of, this is just a person standing on the ground looking up, right? And so we all recognize what the horizon is. Oh, just a second. There we go. All right. I'm almost there. There we go. So this is a person standing, looking up, and the point directly above your head, wherever you're standing, is your zenith. Everybody has a zenith and a horizon. When you look out and you look at where the Earth meets the sky, that's the horizon. And the point directly over your head is your zenith. Let me scroll back up here just a couple. Here is the Earth, and this thing around the Earth is the celestial sphere, and you can sort of get a picture of this now. Here's the Earth spinning. There's the person standing on the Earth. This is obviously not a scale drawing, right? But a person is standing wherever they live on the Earth. You can see the Earth's equator. We know that the Earth's axis is tilted. The tilt angle is 23 degrees, and you say tilted with respect to what? Well, with respect to its orbital plane, this red circle that goes around the celestial sphere. So you see two circles now. You see this big circle that goes like this. This is the celestial equator. It's the projection outward of the Earth's equator, which you can kind of see as the dark blue line there. And then the red line is called the ecliptic, and that's the path of the Earth's orbit. That defines the plane of the Earth's orbit around the sun. So if I go up a couple of pictures here, you'll see this is the Earth going around the sun, right? And you can see that the Earth's equator, which can be seen in each of those little Earths, is tilted with respect to the plane of the Earth's orbit around the sun. Obviously, once again, this is not a scale drawing. The sun is not smaller than the Earth, of course. But this is to give you a picture of sort of the geometry of this. The Earth's axis is tilted, and the angle of the tilt varies, but it's about 23.5 degrees with respect to the perpendicular to the plane of the Earth's orbit, or also called the orbital plane of the ecliptic, right? And so sometimes it's just called the ecliptic plane, sometimes it's just called the ecliptic, but it's the plane of the Earth's orbit around the sun. Okay, and so if you look sort of closely with these lines drawn up on a close-up view of the Earth, you can sort of see the Earth's equator is tilted here, perpendicular to the rotational axis of the Earth, and the orbital plane, the so-called ecliptic, is horizontal in this drawing. And so that should give you a picture. All of these tilts and angles and so forth is what made it very difficult for people to figure out why things look the way they do when you're standing on the Earth. Of course, you know, here's Oklahoma somewhere in the middle of this picture, right, almost right on that axis there. And if you're standing here, then as the Earth turns, you see a different portion of the sky over the course of an evening, right? And that appears to you, it appears to you that the sky is rotating the other way. And so if you were to just take a camera and freeze it, and take a long-term exposure from wherever you're standing, you would see the stars sort of making circles as the Earth turns, but it appears to you that the sky is turning in the opposite direction. You see yourself as stationary all the time, and it appears that the sky is going the other way. And so if you were to take a camera and just aim it at, say, the North Star, which is up here, where I have my little cursor, and leave the shutter open for a long time, the stars would appear to make streaks, with the North Star being at the center, and the farther a star was away from the center would be the bigger the arc it would make. Right? The longer the length of the arc, they would all make the same angle, but the longer the length of the arc. Notice that some stars, the North Star would just stay there as the Earth turned. The North Star is never below the horizon. And in fact, there are a lot of stars that are never below the horizon. They'll just make circles wherever they are. Those are called circumpolar stars. And how many circumpolar stars you have is determined by what your latitude is. If you're Santa Claus and the North Star is directly over the top of your head, then all stars are circumpolar, all the stars that you can see. But if you're living on the equator, then all the stars appear to be rising and setting perpendicular to the horizon. So let me go back to my notes a little bit here. So we've talked about the polar axis. The Earth rotates about its axis, right? The rotational axis, the so-called polar axis. We already talked about the zenith. So the meridian is the line connecting the north celestial pole to the south celestial pole through your zenith. And so the meridian is just an imaginary line that splits the sky in half, east and west. It runs from the North Pole through your zenith to the south celestial pole, and so it splits the sky right down the middle. When the sun is on your meridian, that's called local noon. It's when the sun is halfway between rising and setting. Now we do different things with our clocks now so that we can have time zones. But back in the old days, when the sun was at the halfway point through the sky, they called that noon. So over the course of the day, the sun and the planets and the stars rise and set. They come up above the eastern horizon and set over the western horizon. In fact, what's really happening, as we showed in the picture a minute ago, is the Earth is rotating in the opposite direction. And so the stars appear to be rising and setting, and the sun and the planets, they all appear to be rising in the east and setting in the west. But in fact, what's actually happening is that the Earth is rotating in the opposite direction, and so we're constantly turning toward the east, seeing more and more stars rise above our eastern horizon. I don't know why it keeps coming up like that. that to stay away. So you can kind of see from this picture, this is for somebody who's standing on the North Pole. They would see the stars over the course of a night just appear to be circling, making giant circles around the zenith, because the North Pole is at the zenith. Somebody standing on the horizon, on the equator, would see no circumpolar stars. In fact, the North Star would probably be too hard to see, being right on the horizon. And all the stars would appear to just be rising and going over the top of you and setting. If you're somewhere in between, like we are in Oklahoma, some of the stars are circumpolar. That is to say, they stay above the horizon the whole time. And some don't. And so it just depends on what your latitude is as to how many. This is a complicated picture, but let's just talk about it for a second. So I've got to get my angles right here. This is a picture of the celestial sphere that is broken up into constellations. And so I'll just talk about a few of these. So it's a complete sphere, and every region is in the sphere is in some constellation. Many of them are just historical. They're defined through historical contexts. And so here's Hercules and Lyra and Draco and Corona Borealis and Serpens and Ophiuchus, and many of them I don't know. You can sort of see the plane of the ecliptic, which is this dashed line in the back here, has the constellations of the zodiac. It looks like here's Gemini and Taurus and Aries and Pisces. And if you come along down through here, well, it's too hard for me to follow. Here's Leo over here. Here's Libra. I can't quite tell. Here's Sagittarius down here. And so this is the horizon, this solid line here cutting through here where the person is standing. And of course, here's the equator, the celestial equator, this line here. And so this is sort of an outside view of the celestial sphere as we sort of normally see it. Over the course of the year, as the Earth orbits the Sun, as shown in this picture, then the Sun, as seen by us, moves through various constellations. In June, the Sun is lined up with Taurus. In August, it's lined up with Cancer. In September, I guess, it's lined up with Leo, and so on as we orbit it. And so that's how we get the constellations of the zodiac, or the signs of the zodiac. It's whatever constellation the Sun is in at that time of year. Astrology is associating some effect of that on people's lives, positions of various celestial objects in various constellations. Again, not a science. So let's talk a little bit about how we measure positions in the sky. So you might remember that if you want to measure position on the Earth, you use latitude and longitude. And so the latitude measures the number of degrees north of the equator or south of the equator. So these would be south latitude, these red horizontal lines, and these blue horizontal lines would be north latitude. Weatherford, Oklahoma is about 35 degrees and 33 minutes north latitude, so somewhere in right where that crosshair is. And similarly, longitude is measured east-west, and so each one of these vertical lines is at the same east-west angle, measured from Greenwich, England, which is the 0, and so these red ones are west longitude, and the blue ones are east longitude. And so you can identify any place on Earth by its latitude and longitude. We're 35 degrees 33 minutes north latitude, and 98 degrees and 4 minutes west longitude, and that gets us right to that spot roughly. And so we want to do something similar for the sky, and of course we could just project outward the latitude and the longitude onto the celestial sphere. The problem is that the Earth is rotating, and so a different star would be over the same latitude and longitude, just like here in Weatherford, Oklahoma. Every night, throughout the night, they would constantly be moving through, and so it's not a very good way to identify using latitude and longitude. So instead we use something similar. We look at the celestial sphere here, and we project outward from the Earth, and we devise some angles. And so if you look at this picture, we start with, let me just look at this point. So this is where the sun is on the vernal equinox. And so we use kind of that as a sort of the 0 angle. And the celestial equator, which is the white dashed line, as the 0 for latitude, and then we can the vernal equinox is the 0 for longitude, and then we can define our angles this way. We can measure up from the celestial equator. That would be our latitude. We call that declination. So on the celestial sphere, latitude is called declination, and longitude, which is how far you are from the vernal equinox angle-wise, on the celestial sphere is called right ascension. And so instead of latitude and longitude, we use declination and right ascension. So we divide the sky up into constellations, and here is the constellation Orion. You probably have heard of it. You might even recognize this collection of stars. By the way, a collection of stars is called an asterism. And so this collection of stars that make up the Hunter Orion is called an asterism. The constellation includes all of the stars in that region that's outlined by the shape of the constellation. And so a collection of stars within it is called an asterism. There are 88 total constellations in the sky. We will probably talk about a dozen or so of them. There we go. So if you go out at night and just look at the stars appear to be rotating around the Earth every 24 hours. They rise and set as the Earth goes around the sun. And this is why ancient people saw the celestial sphere is rotating around the Earth. The Earth rotates on its axis as it orbits the sun, and it takes 24 hours to rotate on its axis. And so it looks like the stars are going around the Earth about once every 24 hours. And so the ancient people thought, well, this meant the Earth was at the center of the universe, and it was all going around us. This isn't quite what's happening, of course, as we know now. And but we still see the fixed stars against the celestial sphere. The constellation Orion always looks like Orion. Leo always looks like a lion. Taurus always looks like a bull. All those stars stay the same relative to each other. But when you start looking at the sun and the moon and the planets, they're doing something a little bit different. Over the course of a year, the sun wanders through the sky against the background of the stars, against the celestial sphere, because what in fact we're doing is orbiting the sun, and so it always looks like it's in a different direction. It looks like it's moving through the constellations of the zodiac. The moon, of course, orbits us once a month, and so it appears to move around the sky or across the celestial sphere faster than the sun does. And the planets are doing something a little more complicated because they're orbiting the sun, and so we see some interesting motion. The word planet comes from the Greek word for wanderer. All the stars were fixed except the planets, and so there was a time where the sun and the moon were also considered to be planets because they appeared to the Greeks to be wandering around the sky just as the things we call planets today do. And so the sun appears to, of course, go around the earth once a day if you're an ancient person. But it's actually slowly moving eastward against the background of the celestial sphere so that it goes all the way around in a year. That's, of course, those two effects are one, us rotating on our axis every 24 hours. That's what makes the sun appear to go around us once a day. But also we're orbiting the sun once a year. And so those two effects make the sun look like it's going around us every day and look like it's moving around the celestial sphere in about a year. The moon does something similar. It also appears to go around the earth about once a day for the same reason the sun does, the fact that the earth is rotating on its axis once every 24 hours. But it also appears to go around the celestial sphere once every 30 days, approximately, the time it takes the moon to make one orbit of the earth. And so, in fact, the moon drifts eastward about 12 degrees a day, so that over the course of the month it's gone 360 degrees around the earth, around the celestial sphere. The planets, just like the suns, are slowly drifting eastward. This is called prograde motion against the celestial sphere, but occasionally, for short periods of time, they drift westward. This was very confusing to ancient people, but we'll talk about it more as we go, and I'll give you some pictures of it. We've already talked about the constellations a little bit. I wanted to give one other little tool here you can use to to measure angles. So if you take a pinky and hold it at arm's length, so all the way out, your arm completely stretched out, and measure it against something, that pinky tip is about 1 degree wide. If you use 3 fingers, that's about 5 degrees, 3 fingers flat on. So from here to here is about 5 degrees. And so you can hold something up against again, your arm has to be your fingers have to be at arm's length away from you. Some people have wider fingers, but they also probably have longer arms. And so this is just a rough gauge. But so a pinky tip is 1 degree. 3 fingers is about 5 degrees. A fist is about 10 degrees. Longhorns, tip to tip, so from here to here, is about 15 degrees. And thumb tip to pinky is about 25 degrees. And so you can measure things in the sky, the angular size of things in the sky. Again, in all of these cases, you're holding your arm at arm's length. You're holding this thing at arm's length. So people with shorter arms will get about the same angular size because they'll have smaller fingers and shorter arms. So it'll be a little closer and a little bigger, and those somewhat compensate each other. This is a nice one because this is sort of a measure of how far away Mercury gets from the sun in an angular sense. And so if you were to go out at sunset and put your thumb just above the horizon as lined up with your eye, then your pinky tip will be about as high as Mercury gets after sunset. And so Mercury is an easy planet to see, but almost no one sees it because it is either up just before sunrise or up just after sunset and just for a little while. And so, okay. Anyway, those are useful tools for observational astronomy. We'll talk about observational astronomy as we go. There we go. So we're going to talk a little bit about ancient astronomy, which is how ancient people solved the puzzle that we're talking about now is astonishing to me. People who lived 5,000 to 10,000 years ago made some really interesting observations. The earliest recorded astronomy work we have was by the Babylonians at about 3500 BCE, so 5500 years ago. Already the ancient Egyptians had a 365-day calendar 3,000 years ago. It was based on the fact that the star Sirius, the dog star, the star in Canis Major, Sirius is the brightest star you can see from Earth. The dog star went through one cycle every 365 days. In other words, it was say rising with the sun on the horizon, on the eastern horizon, and then 365 days later it was back to that spot again. And they figured out that cycle they correlated that with a year and built their calendar around that and got about 365 days. And so that was a great discovery. It corresponded, the position of Sirius, this repeatable position of Sirius, corresponded with the seasonal flooding of the Nile. And that has a lot of interesting historical implications, because the Nile River, its flooding, caused people to study geometry a little more, because property lines had to be redrawn after the floods. And so the ancient Egyptians and ancient Greeks were pretty good at math, driven somewhat by their desire to own land. Chinese astronomers recorded comets and novas and sunspots 1,000 to 2,000 year BCE, so 3,000 to 4,000 years ago. Mayans developed accurate calendars based on Venus 1,000 years ago. Polynesians learned to navigate precisely by the stars in open water in the oceans. Another just astonishing accomplishment. They could travel for hundreds of miles in open water. In Britain, of course, Stonehenge and other stone circles were used to keep track of the motions of the sun and the moon, and that was 2800 BCE. So I'm going to talk a little bit about the ancient Greeks, who really broke the back of this problem, got some stuff right and some stuff wrong, but made some astonishing accomplishments. For one thing, they began to understand that the Earth was round, and that's a shocking discovery, especially since some people can't learn that today. One of the reasons they believed it to be round was, as you went north or south, different stars were overhead stars versus different stars would be at your zenith. So as you march north, the North Star would rise in your sky, become more and more, get to a higher and higher angle. And as we move south, it would get lower and lower. And that made them think they were walking on a curved surface. And another big one was they could see the Earth's shadow on the moon. A lunar eclipse is when the moon passes into the Earth's shadow. And so let me just pull up one of these pictures real fast. So here's a lunar eclipse. And you can sort of see that, that there's a bunch of stuff going on there. But the shadow of the Earth on the moon is curved in all of these pictures. It's in totality in the center here, but if you look at these other areas, this shadow is curved, and they figured out that was the shadow of the Earth. And no matter when a lunar eclipse happened, either before or after, there would be a curved shadow there, and they decided that meant the Earth had to be round. That was just another reason they gave. That's just a very impressive discovery to me. Here's another picture of it. Somebody has taken a montage of those shadows and drawn basically what the Earth's shadow looks like, just from taking different pieces of lunar eclipse and stitching them all together. So they knew it was round. Pythagoras, if you remember the Pythagorean theorem, Pythagoras figured out that the Earth was round. And he was teaching that in schools 500 BC, and we had to relearn it after the Middle Ages because people didn't understand it. The ancient Greeks measured the circumference of the earth, and I'm going to show you just a little bit of that. So the first thing I have to say is that, as you get farther away, the rays of light from an object at position A, B, or C, as the object gets farther away, become more and more close to parallel. Here there's a big angle between these two rays leaving from A and hitting the earth. And you go to B, the angle between them is smaller and smaller and so on until when you get really, really far away, like 100 million miles where the sun is, now the rays are almost parallel. And so Eratosthenes, an ancient Greek mathematician and scientist, wanted to figure out how big the earth was. And he sort of did one of the most clever scientific experiments that's ever been done, probably. He said, look, if you look at this picture, he noticed that on the summer solstice, the sun at noon, the sun shone straight down a well in Syene. And so the rays of light from the sun at noon were going straight down the well. Ignore this ray here, this angled ray. This is a poorly drawn diagram. If the sun's really far away, as we mentioned earlier, all the rays are coming in parallel. And so in Alexandria, he erected a pole. And he showed that in Alexandria, on the same day at the same time, the rays were not coming straight down the pole, they were making an angle. And that angle, he measured it, was 7 degrees. And so the rays from the sun were coming in at 7 degrees, whereas they were coming straight down the well in Syene. And so he said, look, that means there's 7 degrees between these two radii from the center of the earth. And that's because this ray, which you could imaginarily continue here, and the ray that goes down the well are parallel, and this line cuts those two. And so the angle here and the angle here have to be the same. And so he said, look, I can measure this angle and it's 7 degrees. He knew there was 360 degrees in a circle, and so he knew that this distance between Syene and Alexandria needed to be multiplied by about 51 or 52 to get all the way around the earth, because 7 degrees times 51 is 357 degrees or something like that. So he multiplied this distance between the two towns by 51, and he said that's the circumference of the earth. And he was pretty close to right, much more right than Columbus was, for example, or any of the astronomers who came 2,000 years later. And it was the simplest experiment. It was just a very brilliant, simple experiment. And so Eratosthenes, by the way, is also famous in the computer science world because he developed a way to produce prime numbers. And so computer science students will sometimes write a program called the sieve of Eratosthenes. So he had two huge discoveries that are still talked about today all the time. And yet he was called Beta, the Greek letter for B, because the smartest guy in his town was Archimedes, who was even more famous. So how would you like to have been around to have ideas that lasted 2,000 years and still be the second smartest guy in your town? That was Eratosthenes. They used this and some other measurements to show, to learn, once they knew the size of the earth, they knew that the moon was about a quarter as big from the shadows that we looked at earlier, and so they knew that the earth was a quarter the size of the moon was a quarter the size of the earth, and they used a little more geometry to figure out the distance to the moon. And so the ancient Greeks knew the size of the earth, the size of the moon, and the distance to the moon. And they even estimated the distance to the sun and the size of the sun using more geometry. They didn't do a very good job of that part of it, but they did determine that the sun is bigger than the earth. And that was an enormously important discovery on their part, because nobody believed that before then. And so it was the beginning of the steps towards putting the sun at the center of the solar system. So that was Eratosthenes. Another great discovery was by a guy named Hipparchus, who figured out that the earth, the Earth's rotational axis is precessing. If you've ever seen a top laying on its side, so I don't know if I can do a little drawing up here, but tops, when they spin, they'll start to do this, right? If they're spinning around, and that's called precessing. And the Earth is actually doing that. It has to do with the fact that other planets are pulling on the Earth, causing it to have some weird twisting motion. And so the Earth's rotational axis takes about 26,000 years to do a circle. And right now, as you can see in this picture, it's pointed towards Polaris, but 13,000 years from now, it'll be pointed towards Vega, which is 46 degrees away, right? This angle here is 23, half that. And so it actually tracks out a circle. And Hipparchus figured this out because he noticed that the Babylonians, thousands of years earlier, didn't have the same North Star in their star charts. So he was very clever. So a little more ancient astronomy. This is what we call retrograde motion in how we understand the solar system now. So here's the Earth's orbit here. Hang on a second, I've got to get there. There we go. Here's the Earth's orbit here. At successive, maybe this is once a month or something like that. And here's an outer planet, also at the corresponding times. And if you look at that planet against the celestial sphere, against the background of stars over here, when we're at position A, that's where we see the planet. And then we're at position B, we see it up here. It's tracking eastward, which is what they normally do. And then at position C, suddenly it's starting to go backwards. And then it goes backwards again at position D. And then at position E, it starts to move forward again. So this business where it's moving up on this picture is eastward. And then it tracks backwards for a little bit. And then it goes eastward again. The eastward motion is called prograde motion. And the westward motion is called retrograde motion. And the retrograde motion is a short period as the Earth is sort of zipping past on the inside lane. We only see retrograde motion in outer planets. As we pass them in orbit, the closer you are to the sun, the smaller your orbit is, the faster you go. And so you might see this when you're going down the highway as you pass a car against the background, against the stuff in the background, they appear to be going backwards. You can kind of fool yourself into thinking that. And so the ancient Greeks were trying to develop a model where all the planets orbited the Earth, and you could still see stuff like this, because they were aware of retrograde motion, and they wanted to be able to explain it. And so this is what the ancient Greeks did. They came up with a model. There we go. Where this is sort of complicated, but I'm just going to talk about it this way. The Earth is at the center. These are just other points. The Earth is actually off-center in their picture. But let's just set that aside for a little bit and say, look, the planet is orbiting in this circle called a deferent. A deferent is the orbit of a planet in the Greek model around the Earth. And then normally that's the simplest explanation for them. That is to say, all the planets are orbiting the Earth, which is at the center of the solar system or center of the universe. Right? But in order to get this retrograde motion in, they had to make these little things they called epicycles, so that it's the epicycle that's going around on this deferent, and the planet is moving around in a circle on the epicycle as the epicycle goes around the Earth. And so occasionally, like when the planet is over here, it's going backwards. And so this was the Greek explanation for retrograde motion. They had this complicated picture where there's an epicycle going around on a deferent, and the planet is going around on the epicycle, and it occasionally backs up. These extra points in here were designed to make allow the planet to be farther or closer, because it was clear even to the ancient Greeks that sometimes planets were closer to us and sometimes they were farther away. These are the signs of the zodiac. This is a picture we looked at a second ago. So let me pull up a few more pictures here. This is how we determined the distance to the moon, how the ancient Greeks did. They knew the size of the moon. You can see here. And what they did was they would hold a coin or something at arm's length, and then so that it was just the right distance and size to blot the moon out exactly. And that gave them similar triangles. This triangle here, this small triangle with the coin, and the big triangle with the moon are similar. They have the same angles, if you remember your geometry from high school. And the ratios of corresponding sides of similar triangles are equal. And so they knew this diameter of the coin, and they knew the diameter of the moon from the experiments I told you about earlier. And so that would allow them to calculate the ratio of the coin to the moon's diameter was the ratio of the distance to the coin to the distance to the moon. And so the only unknown there was the distance to the moon, and they were able to calculate it. And they did a similar experiment to get the sun. And I won't talk about that too much, but that was here's the geometry of that one. And so all of these, they were doing little geometric tricks to figure out the angles and distances so that they could measure the sizes of these objects and the distances to them, and they did a pretty good job. They were way off with the sun. They were pretty close with the Earth. They were very close with the Earth's size. They were pretty close with the size of the moon and the distance to the moon. They were way off with the size of the sun, but they got a really big sun, which was important. I think they got the sun to be about 5 times bigger than the Earth, size-wise, and it's actually about 100 times bigger. But no matter, at least they got it bigger. Okay, I'm going to stop there for a few minutes.